Hello, everyone. Thank you very much for being here this afternoon in Brazil. It's a pleasure to have our guest today, Professor Luis Guilhermo. He's a very nice friend. Many Brazilians know him very well. He attended a couple of conferences in Brazil. And it's a really pleasure to introduce Professor Luis Guilhermo today. Professor Luis Guilhermo is has his engineering degree by University of Costa Rica, master and PhD from the University of Nevada, Reno in the United States. He's professor at the Civil Engineering School at UCR. He has about 180 scientific publications. He's also the vice president of the International Society of Asphalt Pavements, ISTE, former chairman of the Heavy Vehicle Simulator International Alliance, and member of TRB, also editor at the International Journal of Pavement Engineering and Road Materials and Pavement Design journals. So with that, Luis, thank you again for your time. Please, the floor is yours. Thank you so much.
Thanks so much, Camila, Alberto, all the friends from Brazil. I have a lot of friends in Brazil, and I've been there, I think that for now, 4 or 5 times. Pretty happy of being with all of you. I'm going to share my screen. I'm going to look for my presentation. It's a real pleasure, really, to be with you, with all of you. Okay, can you see it, Camila?
You stop it sharing your screen. You have to share it again. I guess you click it, the left button is the right one.
Okay, let me see.
We saw it and you just close it. So you did it the right way the first time.
Okay.
Now we can see your screen. And it's the oculta.
Okay, can you see it?
Yes. Can you press just oculta so we cannot we don't see the Google Meet?
Yeah, ocultar. Okay.
Good. Perfect. Thank you.
Okay, thanks a lot again for being invited. I am deeply flattered about it. Always is a pleasure to talk to a lot of friends in Brazil. Let me check my time. I'm going to talk about accelerated pavement testing as a tool to improve pavement engineering, a successful case. This is based on the work that I did while I was still at the National Laboratory of Materials at the University of Costa Rica, the LANAME. I am still professor at the University of Costa Rica. There is no more experiments run after I left the lab, but there is plenty of information that I can share with you, and there is still a lot of things that we can do with the data that was developed through the 5 years experiment that I'm going to talk about. Well, here is the same mini bio that I sent to Camila. Again, very happy to be with all of you. If you want to meet me or contacting me, there are all my signs, Twitter, my professional Facebook. I have a YouTube channel. I hear either my University of Costa Rica email and my Gmail email, and of course, the professional network LinkedIn. Also, I am always posting technical things. So we are going to talk about pavement design. Most of you are related to that. Most of you do a lot of research. Maybe you have been in the field, in the industry, working at the government. We are talking about a structure that has pseudo-constant loads. And the concept of perpetual pavements are extremely costly. And this is very related to how we perform the design, how we consider the variables we have, how we consider the various inputs for the design of a pavement, and how we perform or how we analyze that design and try to predict the service conditions of the pavement. So there are some characteristics very important. Pavements are constructed over huge distances, different weathers, different subgrade conditions. We can see here the pictures. You see the pavement in the upper part of the pictures is a truck that basically was sunk into a very icy condition, into the snow. In my case, in Costa Rica, and also for you, of course, we have to design pavements in the rainforest, on the tropical condition. But also there are a lot of fellows, a lot of friends that have to design a pavement in the middle of the desert. So it's very difficult to apply the same methodologies mostly with the same properties, or using models that were calibrated in another countries in every different condition or in every different situation. And this is part of my introduction, because this was the decision that I had to make almost 12 years ago, to develop an accelerated pavement testing program at the University of Costa Rica, with all the expensive that it might be. And mostly it's more expensive if you don't have the good conclusion from the experiment. So materials and their properties vary geographically. It's not the same to have, I don't know, a sandstone, or to have a normal rock, andesite from another source. So we need to have very good characterization of materials. We need to know what is the different soil condition we have. And the situation is that normal testing is very limited to predict the in-service pavement structure performance. It's not easy to link some of our usual quality control tests or material design testing to what is going to happen really under field conditions. It's not the same, because we, at the lab scale, we have everything controlled. We have temperatures control, where you can simulate maybe freezing conditions, maybe some moisture damage. But we know that in field, the conditions are going to be different. Also, the nature of the load, we can apply, I don't know, Haber-Sein style, sinusoidal style of loading. We can apply confining stresses, but the real situation on the field is very different. So this is the reason when you start developing an experiment like that, an accelerated pavement testing type of experiment, you need to think in all those variables in order to justify the big amount of money that an experiment like that costs. The other thing is monitoring pavement performance through the performance life is very costly and takes several years. And all of us have worked maybe sometimes or several times with the LTPP database. Right now it has like 30 years of monitoring. The first data that was used to calibrate models start having like a better result when the LTPP has 20 years. So of course, all of us would like to monitor a pavement all during its service life. Of course, we would like to have even instrumentation. In Costa Rica, we have like 6 or 7 places where we monitor different pavements with in-field instrumentation. But what is the real cause of that? And you need time, and you need to be maybe support. Maybe you might have support from the government. because it's a very 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 long time that you need to keep monitoring everything. So you need money, a lot of money through the time. You need to have you need to be committed to the experiment. You need people very well trained. You need to have databases, etc. So the premature failure in a pavement is extremely costly. Having fatigue cracking, having moisture damage is not good. The other thing is, all the time, we have seen several changes in our industry the last 15 years. Now we have warm mixes. We have full depth repair, a lot of it. We have warm mixes, as I already said. We have a lot of semi-warm mixes also. Now we have those big machines that produce foam asphalt. So how do you design using the current models for all those new technologies? So how do you know that this technology is really going to perform well on field conditions? So the accelerated pavement testing might give us a response about that. And this is the reason that I have this famous phrase from Derek Curtis' book, is if you think that education is expensive, try with ignorance. I always give this story that I have here from Costa Rica. While I was still at the University of Costa Rica, in the last 3 years, I analyzed about 15 liquid additives for soil stabilization. And the sellers claims that their product was the best around the world. It can work in any type of soil. But while we do the testing, we realize that only one of the 15 products that we study works well for some Costa Rican soils. So if we try the other products, there was going to be a premature failure. And this is something that we don't know because it's very costly. It's very expensive. So looking for answers. How, and this is another thing, maybe Camila and Tiago might remember that. I started talking about in 2009, while we were at the SILA in Rio, 2011, sorry, with Dr. Witzak of calibrating empirical mechanistic pavement design guide for Costa Rica. Dr. Witzak liked a lot the LTPP, but I told him, Dr. Witzak, we cannot work with developing an LTPP and wait 20 years. I need to solve it now because I want that Costa Rica have its own ME design method. So this is one of the reasons that we start looking for answers. And we realized the accelerated pavement testing has been a source of responses for several years. And there is not only the famous experiments of the ISTE in the 1950s, late 50s, we found that there is a lot of experience in the world, well, not maybe in all the places, but there is enough and sufficient scientific data on how to use the APT experiments and how to implement that in Costa Rica. So just to start, there are 4 types of APTs. The more famous, or well, maybe not the more famous, but very useful, and the first one were the circular ones, like the ones right now in the former Pontes Chaussee. Now the Gustave Eiffel Institute in France is very famous. And we have others around the world. Actually, the National Autonomous University of Mexico, the UNAM, has a very successful experiment in a circular type of APT during the 50s and 60s. They sort of calibrate a very good ME method back in those years. Also, we have the circuits, very famous, like the ISTE. You can see the picture in the upper right part of the slide. Also in the center, I have one is very famous, the NCAT, the National Center for the Asphalt Technology of the University of Auburn in Alabama. Is a great experiment, very expensive, but very good. Also, we have the one from with the Spain flag, that is the SEDEX ones, pretty famous in Latin America. A lot of people from the Latin American countries were to study at the SEDEX and in other times. We can see another from Canada. Also, we have the fixed lineal. I know that you know the one with the Brazilian flag over there. All of you, I studied this experiment a lot for my master thesis. And you can see other fixed lineal devices to perform APT. And the mobile lineal, that basically in the world, there right now are three types of machines. One is the heavy vehicle simulator, the HVS from Dynates, the one that I bought 9 years ago for the University of Costa Rica, the one in the corner in the left-hand side, that is very used, like in 20 or 22 countries. Also, there is the MLS, also the South African technology, is a very good device also. And the Atlas, that there is not like a lot of machines of Atlas around the world, but still is a very good device. Is used by the Federal Highway Administration, and also there is one in the University of Illinois in Urbana-Champaign. Dr. Imad Al-Qadi has done a lot of research with that. Also, Dr. Errol Tutunuer, good friends of us. At the PAVE Lab, the name that we gave to the LANAMES experiments, we started working in 2011, and we developed basically the infrastructure that you can see over there. I'm going to explain a little bit the various details and the results of the experiment. Basically, we have 20,000 bidirectional slow repetitions per day. We selected the carriage speed of 10 kilometers per hour. We apply for each experiment in general 4 loads. I'm not going to explain this in this presentation, but if you want to know, I can explain you later. Well, basically, the idea is you need to perform accelerated pavement testing using the damage concept, because if you use only the normal 18,000 and you divide it in half, so 9,000 pounds load of ESAL, you are going to last forever doing your experiment. So you need to accelerate the damage and use some mechanics to back calculate or to do or to look for the equivalency in ESALs of the experiment you perform. So normally you start with a load 40 kilonewtons, and you start increasing the load through the experiments. This is a whole idea that I can explain it in another moment. We use this type of tire, the dual 11R22-5. We apply wheel wandering 100 millimeters along the wheel path. It's very important to apply it. It depends on the experiment you want to run. For example, if you're looking only like a performance test of permanent deformation, you can avoid to use wheel wandering. But if you want to simulate real load condition, it's very important to have wandering, because you are going to magnify. If you don't have wheel wandering, you are going to magnify the permanent deformation. At the beginning, we use the test in dry condition. After that, we use it under wet conditions, and we compare. And basically, the machine works 23 hours, 7 days a week. Maybe I am exaggerating a little bit, but you cannot have an APT experiment and run it once in a while. If you are going to do this huge investment, you need to take a lot of advantages of the experiments, and you only are going to see the benefit cost ratio if you have this machine working every day, Saturdays, Sundays, holidays. This is the only thing of having a good benefit cost ratio for this type of experiment. This is the initial experiment we developed at the University of Costa Rica, 4 pavement structures with the typical conditions for Costa Rican pavements, 2 thin layers of 7.5 centimeters, 2 thick layers, for our case, 12 centimeters, is the test track AC3 and AC4. And we also use a cemented base and a granular base of 25 centimeters and a sub base of 30 centimeters. We have 2 repetitions in each test track, but the idea was to use one dry and the other wet on the fully saturation conditions for the subgrade. And in the bottom of the slide, you can see our saturation chamber that was used to simulate the water level at the subgrade or wherever we want to measure it, to place it. We have the instrumentations. We have the red ones, you can see, are the typical I-shaped LVDTs. We have the multi-depth reflectometers, the MDDs. We have thermocouples. We also, the yellow one that you can see in the bottom of the subbase and on top of the subgrade is a pressure cell to measure the stresses at the subgrade level. The blue ones are the MDDs, as I mentioned, and also after that, we put also saturation indicators to know what was the saturation of the subgrade, of the subbase, and the granular material or the cemented base. The effective length is, you have to determine that when you are doing an experiment like that. It's very important to know where you are effectively, having uniform conditions on your test section was of 6 meters. And a quick idea of what we do. The first image, because this is the design we did, it was done in 2011. So basically in 2011, we decided what to do. Actually, if you see, at that time, we only thought of having 6 test tracks, not 8. We changed it with the time. We built this huge test pit. It's like a swimming pool, very good sealed, very well sealed. Over there, we put a subgrade. If you talk to your technical engineers, they don't like if you touch the subgrade like that. But in a very rainy country like Costa Rica, where you have the water level very high, if you don't seal very well your test pit, the water level, the national water level is going to mess up your experiment because it's going to produce uncontrolled fluctuations of it. So we didn't want. We place the subgrade, and on top of that, we put the granular base or the solvate, the granular base, the cement-treated base, and the hot mix asphalt layer. It's very important to take into consideration that we use exactly the same construction machines that you use in a normal project. So this is a less variable, that you are taking out of the consideration, because you can do the experiment using another type of construction idea, but it's very good to have the same construction that you have for real field projects. This is going to be is going to reduce your variables. What was the instrumentation? I already mentioned it. Soil pressure transducer, multi-depth reflectometers. The raw surface deflectometers is like a Benkelman beam, but it gives you all the deflection basing. Thermocouples, asphalt strain gauges, or LVDTs, and moisture sensors. And this is the summary of the first years of experiments. If you see, we apply almost 10 millions of loading cycles, and it was almost 71 millions of ISOs analyzed or tested. And if you count all of those experiments, we had 11 different experiments. I'm going to talk a little bit, 18 experiments, and I'm going to talk a little bit about it. So the test development, the RSDs, It's basically a laser that is put over two lasers, measuring in the test carriage. And you can see it over there. Is this type of deflection Benkelman beam. We measure with the RSD every single day, in order to know the damage for each day. We also have falling weight testing, but the situation is the falling weight testing, you cannot move the machine every day to have the falling weight. So the RSD do this work. So basically every day you can know what is the deflection basin, run back calculation, and know every day how the moduli of each one of the layers is changing. Here you can see also the RSD. Sorry, I said laser. No, it's not the RSD. This is the RSD is like a old Benkelman beam, but instead of giving you just 1 point, it gives you the whole deflection base. We also perform deflection forensic analysis for everything. We dig out trenches to see in really what was happening with the deformation of the layers, the cracking, the moisture damage. We tried to assess the exact condition of each one of the layers after the testing. We took course to analyze the moduli, the dynamic modulus, and other testing. We also applied, we did a test on cold mixtures. One is a type of machine that is used to do cold patching, and the other was for surface treatments. It, to do this experiment gave us some problems with the machine, but at the end we sorted out. Also, we do painting analysis of that. It was an experiment that was funded by 3M and other painting companies. Basically, we want to see what happened through the tire movement along these lines, but also for this experiment we apply some temperature. You can see here, this is the result. This is a typical result of painting wearing with the time. So you can see it start low, it has like a maximum value, and with the time it start decreasing. So basically this is what we analyzed when was all those stages of the painting test, just to see, and we translate the experiment into what we thought was a real number of car passes on field conditions. And I put this small chart over there just to show that this was the theoretical performance that was expected, and we did it with our experiment. Also, we work on pavement markings. If you see there, we develop environmental chamber. You can see it a little bit. Over there, we develop with ultraviolet lamps, also some infrared, but not the most important are ultraviolet wavelengths to increase the temperature. It's a very good method to apply temperature. We prefer that instead of the typical frame that this is a conventional oven, because we try to simulate exactly what the sun rays are doing over the pavement. In this case, the road safety companies of Costa Rica hire us to perform this experiment. We apply several passes of the load, and if you can see, the environmental chamber is totally sealed. We put special walls over there. This was a very fine design, and also you can see over there sprinkles. We did not use it for this experiment, but the sprinkles were placed there to simulate raining. So if you can see, we have temperature, a very good temperature simulator using ultraviolet rays. We have raining simulation, and we also have the water table simulation, basically the typical condition for a tropical country, but it's pretty good. Also, we are trying to calibrate the the aging condition using a special device that we developed. Try to understand a relationship between this device, analyzing time of exposure, radiation, and temperature, and try to relate it to our experiment. And we studied the binder oxidation using all the carbonyl and the sulfoxides areas. I'm going to talk about that right now. We also do an experiment on interlocking blocks. It was a pretty good one. And we developed several software tools, our own ones for master course, for multilinear elastic theory, for rigid pavements. And we calibrate the first version of the Costa Rican Mechanistic Empirical Pavement Design Guide. In Excel right now is almost developed, I guess, in Visual Basic, in order to calibrate. I'm going to show you how we calibrate the models. An experiment like that has several main challenges. You need to you need to be very, very careful with maintaining the machine, because since it's a machine that is always moving, you can have tires, explosion, the hose can be loose, and you can have oil spills. You have to be very careful. Right now, we are performing, it's not done yet, the experiment, but it's an experiment with hot mix asphalt, with PET, recycled plastic. The test has been not performed yet. Now, let's talk about some testing results. For example, over there, you can see two extremes. The green, this is the IRI variation after some 1.6 million of repetition. You can see that the variation is very important, and you can see the peak when it starts getting up after some repetitions, or when you start having more damage. This is a very important. For example, you can measure the subgrade pressure. And I'm going to show you two extremes here. The blue one is a very the stiffer section, the one with 12 centimeters of HMA and the cement-treated base. The other two are the granular-based materials. So it's very important to see how the pressure in those is much higher than the pressure that receives the subgrade with the normal material, with the stiffer section. You can see this here as well. The stronger section is the one with the red one, and you see always that deflection in the surface and in the subgrade is always much smaller than the other test section. Also, you can see here how you can. This is a very important thing. This is in the left hand side. You can see a chart where you have how the is a HMA section on top of the cement-treated base. You can see that you start going and doing your low repetition. The HMA has damage, but not really a lot of damage. But the red one is the cement-treated base. So you can see that the layer that is really taking care of the pavement structure, in this case, is the cement-treated base, is the one that is damaged, and this result was confirmed through the whole experiment. Well, here you can see the variation among two different points of a single test tracks. Those different, basically the green dots or triangles and the yellow and the red ones are parts or were measured in two different places of the same test track. And you see why you can explain this difference. It's basically construction differences. So talking to guys like the South Africans, Wynand Stein, Louw du Plessis, Maurice De Beer, or talking to John Harvey, to Dave Jones from UC Davis, to Gusset Chuain from the Florida Department of Transportation, they recommended us to perform different analysis on both sides of this test track. And it's basically because we are assessing a normal thing, because due to different construction conditions, you can have different behaviors in your pavement, and all of you know that. This is a very important chart. Is the same? I'm going to focus only in the one in the right hand side. It's the same what I just talked about it. you can see in blue how the HMA moduli almost did not change through the whole experiment. And you can see this experiment reached 20 millions of repetitions. But the red one is the cement-treated base, and the moduli start decreasing with that time. At the end of the experiment, you still have a very good strength in the cement-treated base, much higher than the sub-base. But you see that damage of this pavement structure was taken by the cement-treated base. But it was a pretty good approach, because based on that, we are going to calibrate the Costa Rica Mechanistic Empirical Pavement Design Guide, not based only in accumulative damage, but also using another concept that is the recursive damage, like the one used by Caltrans, developed by John Harvey and the people, and the one developed by the South Africans almost 30 years ago. So recursive damage, recursive accumulative. What is that? Is to use the real stiffness of the material at each moment of its service life. It recognizes the material has damage through the time. Well, just a picture of how the strains are measured by the LVDTs is in the longitudinal and the transverse directions. It was expected theoretically. And also in the right-hand side, you can see what is happening when the material starts having damage. You can see also the microstrain, the strains on the bottom of the HMA layer, and how it starts behaving weird when we put water at some time of the experiment. But the idea is because we realize that if we throw water on top of the pavement surface, you can see better the cracks with the time. Same happened here. You can see the longitudinal strain start picking up when you have when you start seeing the cracking of the pavement. Here you can see the cracks, basically horizontal. After that, also longitudinal were developed, and you can see over there a measure of the cracks. Also, deflection analysis was performed every day. We wrote a paper of that for the APT 2016, when you can see the falling weight capture only linear behavior, but the RSD and the MDDs effectively can capture the nonlinear behavior of the granular materials and the soils. It also happened through the final condition of experiment. We, as I mentioned, we performed the falling weight analysis at the beginning of the experiment. We ran the experiment, and we ran it again at the end of the experiment when we can move the falling weight. But it's very important when you do APT test. You need to develop database tools and software development to analyze the data. Why? Because you need to take advantage of the huge amount of information. As I mentioned at the beginning, now I am confirming that. With those 5 years of experiments and all the data that we develop, in my case, I can use this data to do different analysis, different research, a lot of simulations for a lot of years, because are millions and millions and millions of data points that you need to properly storage. But not only have it properly stored, from the beginning, you need to be sure about how you're going to storage it, but also how you are going to use it. I'm going to show you right now the end of the presentation, about the various experiments and the various calibration models that you can perform. Well, this is just a calibration methodology. I'm going to explain it. It's basically to have lab analysis and what is happening in your APT test, and you try to relate this in order to adjust the models statistically. Let's talk a little bit about transfer functions. We know what is the various distress mechanisms for fatigue cracking. You know, basically the bottom up one, when you have the maximum strain at the bottom of the hot mix asphalt layer. For the cement treated base, you might have also the analysis of the tensile stresses on bottom of the CTV, and compression stresses for the granular materials and the subgrade. The top-grade cracking, you know, is basically due to, is initiated by the oxygen penetration, oxidation. Weakening analysis or not. In our case, we didn't do that, but we analyzed a lot of permanent deformation. I'm going to show you what were the models developed for permanent deformation based on the different models that we do. And we do, of course, for our HMA material, the laboratory analysis using the typical triaxial test, the repeated load triaxial one. And we try to match the permanent deformation at the lab stage with the HVS stage. And we use shift factor to calibrate models having the lab testing and having, of course, the field testing, because it's very important. This is the typical permanent deformation model that we all know for the MEPDG. We also look for the permanent deformation in granular materials and soils. So we had to perform at lab scale all the test protocols, varying the confining stresses, varying the deviatoric stress in order to have the nonlinear stiffness models for the granular materials and the soil. And this is the model we calibrate. You can see it over there. We also perform fatigue cracking. In this case, we use the 4-point bending beam, and we use plant mix and also laboratory mix in order to calibrate the fatigue on the lab stage and the HVS stage. For the field stage, since we didn't have a real measure of cracks, and it was not easy to measure the cracks, we developed the shift factor or the calibration model using a damage concept that you can see over there. So basically, we determine the damage at each cycle applied at the lab with the 4-point bending beam and the damage at each cycle at the field, taking the damage as the reduction in the dynamic modulus of the HMA layer. So it was the concept. So we put one on top of the other for the plant mix and for the lab mix, and we developed a calibration using the same idea that I already showed you. We performed this analysis that I can show you, that I'm showing you right now, just to be sure that the moduli that we calibrated for the various layers was good regarding their, for example, in this case, this is the strain measurement at the bottom of the HMA. So we tried to see if the moduli that we calibrated was very good to produce the same signal of strain that we developed. So we said, okay, we have a very good match among the theoretical strain signal versus the real response of the real strain signal. So what was the idea of that? To know that we do a very good back calculation of the various layers. With that, we do a calibration for the plant mix and the lab mix, and we realized that the shift factor for the plant mix was 2.5 times, and the shift factor for the lab mix for fatigue was 1.4 times. So basically, using the level of damage that or accounting for the damage, taking the 50% of the initial moduli, we transform our normal model or our data into a normal fatigue model like the one you are seeing in the slide. So basically, the millions of number of loading repetition in millions is equal to this equation that we have related to the strain, to the stiffness, and also to the test temperature that we found it highly significant for our experiment. And you can see over there the various transfer functions we developed for fatigue, for permanent deformation of the hot mix alpha, for permanent deformation of the granular base, permanent deformation of the subgrade. So those are, in the case of the granular base, we include, you can see the various variables, the deviatoric stress, the confinement stress, and also the percent of water, of the humidity of the material at this moment when you are working. It has a lot of lab testing also. It has several master's and engineering degrees thesis. You know, it might be very, while you look at it, it might be, you can think it was very easy, but there is a lot of people of a lot of work or a lot of people behind it. Just for finishing, you can see over there some of my former students. We develop a contact tire pressure study using this special loading weighting device that you see over there. The fastest one. It's a load sail with several small loading sails when you can know exactly what is the pressure at each point of your tire, and you can also know what is the contact pressure at each one of the points. And you can see over there, I presented this work in Doha, Qatar 2 or 3 years ago, where we studied exactly what was happening and how were the various contact stress pressures under various conditions, and we study and simulate under finite element the stress distribution, the moduli change for the bays, for the subways, and other analysis that we perform. We did some analysis with that with Dr. Kim, the former professor of Dr. Tiago Aragao, and we also worked with Tiago for about 2 years with that. There is a PhD thesis based on these ideas, what was a pretty good thing. What is the future? We are thinking in different model calibration for the various distresses that you know. We wanted to adjust to different weather conditions. What happened at high temperatures, what happened on the fully saturated pavement, what happened if you have moisture damage, or you try to accelerate the moisture damage because a lot of raining is falling on the pavement. The Atlantic of Costa Rica is very critical because over there we have our main harbor, so we have a lot of loads, a lot of trucks, a lot of 18-wheelers, fully loaded of, goods and products. It has a lot of raining, so basically over there you have the pavement saturated through 90. So the water, the saturation level is very important, and also there is a lot of the temperature is very high because it's a very very hot weather. So I think this is the other thing that we might start studying over there. Also, of course, calibration for other test tracks with other materials, like recycled asphalt pavements, as I mentioned, plastic sections with asphalt modified with plastic. Also, to me, it's very important because in Costa Rica, we have already machines for foam asphalt. This is very important. And also, there are like 30 sections for our own Costa Ricans LTPP. So, and as I mentioned, like 5 or 6 of them have different instrumentation. So I think it's going to be very important also to link those test sections with the actual HVS or APT sections. So, as we say in Spanish, muchas gracias for your time.
Thank you very much, Luis. It was a very nice and informative presentation. We are receiving, I ask everyone who has questions to post on YouTube so we can get the questions to pass to Professor Luis Guilhermo. We have already a couple of questions. I guess you can stop sharing your screen so people can see you. No, just press ask. Yeah, perfect. So the first question is from Professor Adalberto. He said the accelerated pavement testing facility in Costa Rica is really fantastic. Which effects or factors you were not able to simulate in that facility? Is there anything specific that you think was not possible to simulate from the field?
Low temperature is the only thing that we cannot simulate. But we didn't do anything about that because basically we don't have it.
We have another question from Andre Rosa. He's a graduate student. Thanks, Professor, for the presentation. What are the mechanisms used in your tests for removing moisture content from the subgrade layer when analyzing its effect in the pavement performance?
It's very important. Well, basically we have the saturation chamber, and basically for gravity, we equal one side of the saturation chamber through the level we wanted in the subgrade. So we basically want to have the water level at the top of the subgrade. We measure it. When we realize that it was already soaked, we allow some days just to have the granular base or the granular salt base to soak it by capillarity. So the salt base reach a value of 51%, I think, of saturation, and the base like 30%.
Regarding the moisture on the subgrade, does the soil change a lot in Costa Rica depending on the region?
Yes. Yeah, because people think that we are like, I think same happened to Brazil. People think that we are always playing soccer in the beaches. And you came here, basically we are a mountain country. And we have several types of soils. Every 100, 200 meters, we have different type of soils.
So the soil you have used on the HVS experiment is the same, right?
Yeah, we use only one type of subgrade. It's basically the same subgrade of the University of Costa Rica soil. So okay. The one that we have over there.
Okay, we have another question from João Pioli. Thank you for the great presentation, Professor Luis Guilhermo. I would like to know, how do you convert actual passages of the wheels into easels? Also, do you have a specific procedure in Costa Rica to design flexible pavements based on the accelerated tests you carried out?
Well, we use the concept of damage. The same one that you use to convert is the same procedure that you find in the Jiang Huan book. Basically, we have you convert that relation of loadings, and you have exponent, and you can use 40. That's typical for Jiang Huan, but we use 3 point something related to the fatigue one that we had. So this is the idea. So this is the way you convert to some normal easels to other loading. And yes, we have in the Costa Rica ME, at least as I left it at Laname, there is an initial book where you can, when the people that is designing pavement is able to use the performance models we calibrated.
That's good, very good. Let's see, we have another question from Andrizi, another graduate student. A great presentation, Professor Luis Guilhermo, thank you. Have you already compared results of accumulated damage of the asphalt mixture obtained from the accelerated testing with the damage of the asphalt mixture by using the VECD approach?
No, not yet. But it's easy to do because they might have still a lot of original material for the experiment because it was over there storage.
Good. I'm not sure if is there any other question. Maybe it's coming through YouTube. I have one question. You've mentioned a couple of techniques with respect to cold recycling and use of plastics. Are those techniques already in use in Costa Rica, or is it still a lab experiment?
No, lab recycling is used a lot here, but in a very empirical way. So we are trying to help a lot of that. Right now I have a foot at the at the university, but another in the consultant private work. So we are trying to help people to do good designs with cold mixtures. Right now, there are 3 companies that have the material for the machines for foam asphalt. So we are trying also to help them how to use it very well, and we are using. What we don't have here yet is warm mix asphalt, but cold mixtures and foam asphalt, yes. And I think it's picking up.
And with respect to the plastics, are them already in use?
No, not yet, but we are going to build our first test section very soon. I think before the end of the year.
Very good, very good. Let us know about the results. We are very
there was a
curious
question
about
over there.
That.
There was a question over there.
There is another one. Yeah, there is another one from Professor Adalberto. Is there some way to simulate aging of the asphalt binder in this sort of accelerated testing?
Yeah, right now with the with the aging system we have using ultraviolet lamps, yes. But there is a huge experiment that can be run, that has to be run, seeing the effect of the current test track aging and measure it under the other small chamber that we have. When I left, the experiment was on their running, but I don't know right now, honestly.
You've mentioned also the paintings. Is there a specific, the seasons in Costa Rica are very much different from Brazil, but is there any specific type of painting on the roads that it's more used in Costa Rica, or it depends on the region?
No, they want to use the cheapest one, and this is the reason we did this experiment, because trying to show them that there are other ones that may perform much better.
Very nice. Let me just double check if is there any other question on YouTube. Apparently not. Professor Adalberto put on the chat box, on behalf of the graduate programs in transportation engineering of the University of São Paulo, I thank you, Professor Luis Guilhermo, for your excellent presentation and for the time you dedicated to us. So thank you very much again for your support, for sharing your experience, for showing us this amazing experiment in Costa Rica. I personally saw the device and the facility. It's really, really impressive. So congratulations and thank you again.
Thanks a lot for the invitation, and it has been a pleasure to me.
Thank you. Bye-bye.